In this discussion, we're going to look at how we apply the concepts that we discussed previously to performing calculations. And so just as a reminder, we use the law of mass action to come up with an expression for equilibrium. This is the ratio of our products to our reactants when the system is at equilibrium. Okay, so the thing that we want to remember too is because this is, K is the equilibrium constant, then these values that we use are our concentrations that are at equilibrium. So when the system reaches equilibrium, the value of each of these concentrations, that's what we use to find the value for the equilibrium constant. Okay, so what if we have a set of conditions that are not at equilibrium? Well, we're going to use the same expression that we got from the law of mass action. Okay, so same expression. However, we're going to use, instead of equilibrium concentrations, we're going to use initial concentrations. The only purpose for doing this is that we want to see, okay, here's an example of how that would be applied, but we want to see in which direction is our reaction going to proceed to get to equilibrium. Okay, we set up our system with these concentrations. When it starts and the reaction proceeds, is it going to go in the forward directions? Is it going to go in the reverse direction? And that's the purpose of Q, the reaction quotient. Okay, here's what we can know from Q. Well, if it's equal to K, then we know the system is already at equilibrium. If it's less than K, then we know the system is going to proceed in the forward direction. We use the term shift right for that. It's going to make more products. If it's Q is greater than K, then the system will go in the reverse direction. It's going to make more reactants, or shift left. So let's see how that applies to performing these calculations. Well, here I have a basic list of steps. Okay, and you can pause this and write these down. I think these might be listed in your text as well. But these are this is the procedure that we're going to use to solve these problems. And the nice thing about equilibrium problems are, once you understand the process for doing these calculations, it's the same process each time. So we're going to look at several different types of problems and how we would apply this process. Okay, first off, we're going to, with this problem, we're going to write the equilibrium expression. So I'm going to just put it up here, kind of out of the way. Let's see. So if you are viewing this, you should be well versed in writing equilibrium expressions. And I'm assuming, I didn't check, but I'm assuming this is balanced. Let's take just a quick look here. 1, 2, 3, 4, 2, 7, 10, 4, 5, 6. Yes, okay, so then the acetic acid. Okay, so here's our equilibrium expression, and what I need to find K, that's what we're trying to do, is I need the equilibrium values for all of those. It gives me 1, but the other values it gives me are initial concentration. So let's see what we do. What we're going to do, we call these ICE diagrams. I, C, E. I for initial concentrations, C for change, E for equilibrium. All right, and the way I work these, some people lay them out kind of more vertically, and I think your textbook may do it that way as well. I find this horizontal approach is a lot easier to do, so that's the way I'll be working them. So let's put in our information. What do we know? Well, we know that each has an initial concentration of 0.810 0.810. And in these problems, if it doesn't give you a value for an initial concentration, we're assuming it's 0. Now, since the liquid water, that product, is not in our equilibrium expression, we're going to just line it out there. We don't need to do any calculations with that. It doesn't affect our value. All right, so what else do we know? We know that the acetic acid concentration at equilibrium, so down here in the E row, 0.748 molar down there. Okay, so now, what is this change line? The key thing to remember about the change line is it is dictated by the stoichiometry of the problem. Okay, of this balanced equation. That's why you have to balance the equation first. So this C line here, you're going to be looking at the coefficients in the balanced equation to know what to put in this line here. Okay, now, do we need to find a Q? Well, no, in this case we don't. If I am missing one of the reactants or one of the products, then I already know that it's going to shift in that direction. So in this case, I have no products. So the initial thing that's going to happen is it's going to start making products. So for this one, I don't need the value of Q. Okay, it's going to go in that direction towards the products anyway. So what does that mean? Well, with respect to this change line, if it's going to make products, that means the change in my reactants, they will be decreasing. So it will be a minus or a negative change in my reactants. I'm going to be making products, so it's going to be a plus there. So essentially what you're going to find is that the value of knowing which way the reaction is going to proceed, which way is it going to shift, is so that you know what the signs are on the change line, on this middle line. Okay? So now, well, where do I go from here? Well, look, here I have an initial and an equilibrium concentration for the acetic acid. So I know, or can find, what the value of that change is. So 0.81. Okay, so 0.062 is the difference between the initial and the equilibrium. Now, because it's 1 to 1 to 1, the change, the magnitude of the change, is going to be the same. They have the same coefficients. Magnitude of the change is going to be the same. Then I just combine the initial and the change values to get my equilibrium values. Now that I have these, I'm going to plug those in to my equilibrium expression. And that gives me 0.111. No units. So that's my value of K. So if I have initial concentrations and I have at least one equilibrium value, then this is the way that I would solve that problem. I figure out what the change is and then ratio that in for all the other reactants and products, and then add the initial and the change together to get the equilibrium value. All right, so let's look at another one. Here, it's giving us the K value, and it says 1 mole of each are placed in a 0.5 liter flask at 425 degrees Celsius. It wants the concentrations of those three when equilibrium is reached. Okay, so on this one, let's write our expression. And we're using concentrations here again. So we have hydrogen iodide squared over okay. And now I'm going to write this expression out. See, we start exactly the same way. Now I'm going to plug in my values. I have 1 mole of each, but they're in a 0.5 liter container. So I have a 2 molar solution, or 2 molar moles per liter of the hydrogen and 2 moles per liter of the iodide, and none of that. So we automatically know we're going to be making products, so we can put the sign in on our change line. And it wants to know what are the concentrations of hydrogen iodine and hydrogen iodide when equilibrium is reached. Okay, so here in this problem, we don't have a value of any of the equilibrium concentrations. And so what we're going to do is we're going to say, all right, say the change here on the iodine is X. What would be the change for the hydrogen? Well, they have the same coefficient, both 1, so it would be X as well. And then the hydrogen iodide has a coefficient of 2, so the change there is going to be 2 times X. Okay, so now we're going to get an expression down here where we have 2 minus X, 2 minus X, and 2X. And so we're going to plug that in. When I do that, I get 2X squared divided by 2 minus X times 2 minus X. Okay, so how are we going to solve this? Well, the easiest way, since I have a square on top, square on the bottom here, I'm going to take the square root of both sides. So the square root of K then is going to equal 2X over 2 minus X. Okay, now I have a value for K, so let's plug that in. So I have the square root of 55.64. It's 2X over 2 minus X. And let's go ahead and get a value for that. Or not. Let's just go ahead and I'm going to move over this way to continue solving this. So that gives me square root of 55.64 times 2 minus X is equal to 2X. So square root of 55.64 times 2 minus square root of 55.64 X is equal to, so distributing that through, and I get 2 square root equals and that's going to be a plus that, and then times X. And so let's see what we get with that. That went there. Now we're going here. So I get 1.58 for X. So then I'm going to take this X here and we're going to plug it into the equilibrium expressions up here. So 2 minus 1.58. So I would get 0.42 for the hydrogen. Same thing, 0.42 for the iodine. And 2 times 1.58. I would get 3.16 for the hydrogen iodide. Okay? Alright, now, sometimes we don't always get a perfect square. And so, in this chapter, you will actually get to use the quadratic equation. I'm going to do this one by hand, and I would like for you to at least practice a little bit doing that by hand. You might be a little rusty, but when we're doing the test, it is perfectly fine with me if you use the ACT program on your calculator that will solve quadratic equations for you. Okay, so here we have our expression. I'm going to try to see if I can't get all this in a little smaller space this time. Okay. And I know the value of K, and I know that it's going to be, we're in pressures, and so we have, or no, we're in, yeah, concentrations, PCl3 and Cl2 and PCl5. Okay, and it says the initial concentration is 1.6, 0, and 0, so we know it's going to shift right. So we have a minus, plus, and a plus. And so they're all the same coefficients there. So 1.6 minus x, x, and x. Okay, and so now we have our expression is 1.20 is equal to, we're going to have an x and an x, so we have an x squared, and then here we have 1.6 minus x down here. So let's simplify this. 1.20 times 1.6 minus x is x squared, and 1.2 so 1.92 minus 1.20x equals x squared, and let's make it look like a quadratic form here. X squared, and that would be plus 1.20x and minus 1.92 equals 0. So here's our standard form, A, B, C. Okay, so quadratic, we have negative b plus or minus the square root of b squared minus 4ac all over 2a equals x. So if we plug that in, what do we get? We get negative 1.20 plus or minus the square root of 1.20 squared minus 4 times 1 times negative 1.92 divided by 2 times 1. So let's see what values we're going to get from that. If I do this right, let's see. 2 squared minus 4 times minus 1.92 equals, second, let's get rid of that. So I'm getting minus 1.20 plus or minus 3.02 divided by 2. So we get two values for x, and so we have we get a negative 2.11, or we have a 0.91. Now what we do is we take these x values, plug them in to the equilibrium values, and see if they make sense. Well, one of the things we can't have is we cannot have a negative concentration. So since just x by itself is an equilibrium concentration for our products, we can throw that one out. So we know x is going to be 0.91. So we have 1.6 minus 0.91, which is 0.69 for the PCl5, and then 0.91 and 0.91 would be the equilibrium concentrations of our products. Okay? So, not too bad. Now, sometimes our K values are fairly small, and we'll see this a lot when we get to working with acids and bases and the degree to which they dissociate. So let's take a look at something we can do to possibly avoid having to solve a quadratic. Okay, I know it's real easy to plug these things into your calculator, but it's also very useful to know when you can simplify things so that a quadratic or a cubic or something like that is not necessary. So let's take a look at this one and see what we get. Here we have, I'm going to write this. Again, please notice how I'm doing the same exact thing every time as far as the way that I approach these problems. We always just set up your ice diagram. Okay? I'm going to write my equilibrium expression. This time I know what K is. So I'm going to put it in there. And that's going to be NO squared over N2 times O2. Okay? So now, what do we have? We have 0.8 on the nitrogen is my initial, and 0.2 and 0. And we want the equilibrium concentration. So again, we know it's going to shift right. And so we're going to have X, and then that would be 2X. So 0.8 minus X, 0.2 minus X, and 2X. Okay, now, so think about what does a small K mean, especially one this small. This is telling me that the ratio of products to reactants is 1 times 10 to the minus 5th. What that says is I'm not making a lot of products. Okay? Well, what does that mean as far as our calculation goes? Well, what that means is that this value right there is going to be very small. Okay? Same thing with this one. In other words, the change in our reactant concentrations is going to be very, very tiny. And what we're going to do is we're going to just make an assumption and say, okay, we're going to assume that the change is negligible. In other words, we're going to just say X is 0. X is out there way in the decimal places, not going to affect our calculation if we say that it's 0. Well, if I do that, what do I get? Well, if I plug in those numbers, I get 2X squared over 0.8 times 0.2. Much easier than doing all that work to find out what the quadratic is. So let's see what we get. 1 times 0.8 times 0.2. So I have 1.6 times 10 to the minus 6 is equal to 4x squared. I want to divide that by 4 and take the square root. So I get X is equal to 6.32 times 10 to the minus 4. Okay, so how do I know if this assumption I made, that X was very, very small, how do I know that that's a valid assumption to make? Well, what we want to do is look at what percentage of the initial value is the change. And if we get that it's less than 5%, then it's an okay assumption to make. So for this one, I want to look and see if my X, and we'll use, let's just use our smallest initial concentration. I want to see what that value is. And so when I do that, I get that it is 0.32%, and so it meets the criteria. And so I am okay with using that to find the values, my equilibrium values. Now, when I what you'll see is when if I were to plug that in, again, the change is out there in the decimal places. But I can use it, I mean, if you carry it way out, then you'll see 0.8 minus that X. But the initial or the equilibrium concentration of the nitrogen and the oxygen, approximately 0.8 and 0.2, and then the product, the concentration is going to be 0.001264. Okay? So that's a way to simplify a calculation that could potentially have a quadratic in its solution. Okay, now I think this is the last one, and what we're going to do here's one to show you when do we actually need to calculate and use a reaction quotient, because up till now we've had zeros on one side, and so we knew which way it was going to shift. So let's look at that. Here we have our reaction. Oh, this is one we used before. Okay, so we have HI squared over H2 and I2. Okay, and so let's rewrite it. Okay, so 0.00623 and 0.00414 for the iodine, and this time we have a value for the product as well. So here we have values, initial values for everything. So there is no intuitive way to know which way this is going to shift. So what I'm going to do, I'm going to use those concentrations to find the reaction quotient. And there I get 19.45. Okay, so here comparing this, we know that Q is less than K. Alright, and if you remember, if Q is less than K, it's going to shift right or make more products. So we're going to again have minuses on the reactants, plus on the products. And we have an X and an X and a 2X. So 0.00623, 0.00414, and 0.0224, minus X, and plus 2X. So our expression, 55.64, is equal to 0.0224 plus 2X, 0.00623 minus X, 0.00414 minus X. Okay, and now we definitely have a quadratic in there. We know because the K is so large, we're not going to be able to simplify it. And so since it's the last problem, and the solution from here is math, I would like for you to do some math and come and see me, and I will let you know what the correct answer is for this problem.